All right, so we're going to finish this example real quick. I'm hoping this will be a pretty short computation. So what we have here is the where we ended up so far. I'll scroll up a bit just so you have it for your records once I get a hold of my mouse pointer here. So here was the section that we were looking at, and what we were ultimately trying to do was first off finding the location of the plastic neutral axis. That's where the area on top equals the area on the bottom. Really what we're interested in is where compression equals tension, but since this section has a common yield stress, then we can factor that Fy term out and really only care about is just the geometry, where the area on top equals the area on the bottom. So we developed an expression for the area on top. We just took the area of the top flange and multiplied it by that top portion of the web. So it was 5/8 inch thick, and then the height is 32 minus x. And so did the algebra, and that came out to 30.5 minus 5/8 x. Then for the bottom, we had the bottom flange, which was 18 by 1 1/4, and then the web portion was 5/8 just times x. So it was 32 minus x on the top and x for the bottom. And so do all the algebra and chug that out, and you end up getting x is 6.4. So that's where the location of the plastic neutral axis is. Now, if you wanted to express that from the bottom, just so you're aware, you'd take x plus 1 1/4. And I only mention that because in the slides later, it's expressed from the bottom just to try and compare apples to apples with where the centroid is. Now, where we left off is we were looking at the ZX computation. And so for the ZX computation, what we did is we looked at each shape. We split it up into 4 shapes, and for each of those shapes, we need to compute an area, and then we need to compute the centroidal distance. So we had gotten to the point where we looked at the shape 1 and shape 4 just to make sure that we understood where the centroidal distances were. Now let's see if we can do these middle shapes. So for the web, let's do the top portion first. So the height is 25.6. So 25.6 times 5/8. And so when you do that, this top portion, this is 16. So that's just 25.6 times 16. And for the bottom portion, it's 6.4 times 5/8. And so this ends up being 4. And one of the other things that I think is worth looking at is look at the areas. If you look at the area of 1 and 2, it's 10.5 times 16, or sorry, 10.5 plus 16. And so 10.5 plus 16 is 26.5. 4 plus 22.5 is also 26.5. So we were successful in finding that point where the area on top equals the area on the bottom. So this method kind of serves as a nice check for that. All we have to do now is find the location of the centroid. And so the location of the centroid, so if we look at shape 2, and we're talking about the centroid of each individual shape. For shape 2, it's half of 25.6. So 25.6 over 2 is 12.8. And for shape 3, it's half of 6.4. 6.4 over 2 is 3.2. And so now what we're going to do is just going to do this row by row. 10.5 times the 25, 16, and times 12.8, and so on and so forth. So 10.5 times... So this is 272, and I'll go ahead and write out everything. I don't think you need to be this exact for a calculation like this, but just in case you're following along. This is 204.8. This is 12.8. This is 158.0625. Again, don't think you need to be that exact, but just so you're following along. So this plus this plus this plus that. The sum is 648.4, and so there you go. Z is 648.4 cubic inches. And so I think that the ZX computation is pretty simple. There's a lot less there going on than with the algorithm for the moment of inertia. I find that the moment of inertia is a lot more of an involved computation. I might actually, just for the heck of it, here in a sec, pull that up in Excel just to show you how I would do this in Excel. Now, in order to determine the plastic moment, so the plastic moment is also something that the example asks for. This is really easy. MP is just Fy times Zx. And Fy times Zx, all you do is you take 50 KSI and then you multiply it by 648.4 cubic inches. And so when you chug that out, just multiply it by 50, you get a number, it's like 32,420. And so that's the plastic moment. Just make sure that you're recognizing the units. The units are in inch kips. This is a moment, right? So it's a force times the distance, but our stress was in KSI and our ZX is in inches cubed. So a lot of times if you're looking on the capacity side, if you're just doing the math, the moment capacities tend to come out in inch kips. So if you want foot kips, you need to divide by 12 because 1 foot kip is equal to 12 inch kips because it's just saying 1 foot over 12 inches. So if we divide this by 12, we get that the plastic moment is 2701.67 foot kips. Boom. Okay. While we're at it, since we're here and it's only going to take a little bit of time, I'll go ahead and show you sort of the Excel way of doing the section property computation. I think it's kind of valuable just to show you how to do this because there's a very good chance you might need to do this, maybe in your career or something. So let's copy this. Let's see if we can open Excel. Open up a blank workbook here and let's pull that over. All right, so what we'll do is we'll copy and paste this in, so just so we have it here to look at. And let's see if we can chug this calculation out. So what I like to do is I like to set up a little table, so shape. And you'll need sort of 6 columns from there, A, Y, AY. And so those 3 are sort of about computing the centroid. And then these are about computing the moment of inertia. So we'll do this, AD squared. Okay. Maybe another thing I'll do is I'll take these and I'll make the font a little bigger, make them a little wider. Ooh, not that wide. About like that. That way we can kind of see what's going on. Okay. So what we'll do is we'll have the top flange, the web, and the bottom flange. And we'll need some sums here. And so just to make the table kind of pretty, I've done this enough times so that it might seem I'm doing this kind of quickly. The nice thing about YouTube is you can always just pause it and follow along. In this table, we will need 3 sums. We'll need the sum of this column, we'll need the sum of this column, and we'll need the sum of that column. And you'll see why here in a second, because these two here, the AY and the A, we need that to get the centroid, and then the final column is what we're after with the moment of inertia. Okay, so the first thing we need to do is compute our areas. So we can say 14 times 0.75, 32 times 5/8, and then 18 times 1.25. And so now we have the entire area of the section. And so one of the other things here, we could look and say, remember we were trying to find the plastic neutral axis where the 2 areas equaled one another. So those 2 areas needed to be 26.5. That's what we found when we did the ZX, when we looked at A1, A2, and A3 and A4. The 2 components added up to 26.5. So just another check for you. Okay. For our here, let me turn my red pen on here. But for our centroid calculation, what I'm going to do is express all of my distances from the very, very bottom. So for example, for the bottom flange, how far is it from the very bottom to the centroid? Well, it's just half of the thickness, right? Because we're just going that little half thickness. So 0.5 times 1.25. There's that distance. For the web, again, we're going from the datum, so we go the full thickness of the bottom flange and then half the web depth. So 1.25 plus 32 over 2. And then for Y, for the top flange, we go bottom flange, full depth of the web, and then half of that top flange thickness. So 1.25 plus 32 plus half of 3/4. And again, you can use decimals or fractions, however you want. Okay, and so we do that times that. So this is just AY, AY, AY. So if we want to determine where the centroid is, I'll leave the units off. We just do sum of AY divided by sum of A. Pretty simple. And if you see in the slides, that's what we got. So nothing really, really magical there. Now for the moments of inertia, this is probably the one thing that we glossed over, which, by the way, this part of the video is totally just for your educational experience. We're not going to be doing this on homeworks and exams. I just want you to kind of follow along. If you're ever studying for FE exam, though, maybe this is a good little review because there's a lot of stuff in here that that's kind of worth looking at. For the moments of inertia, we're going to use BH cubed over 12. So the base times the height cubed over 12. The big thing to keep in mind is you have to be consistent. The B is always the X dimension, the H is always the Y dimension. So for example, for the bottom flange, it's equals 18 times 1.25 cubed over 12. So if you're looking at I-beams, what you find is that this value is pretty tiny for the top flange and the bottom flange, but for the web, it's really big, because for the web, the width is the web, and the height is the depth. So that's why for the web, this one's really big, and then this one's just and again, you can always pause and go back and forth. The D values, again, all you have to do for the D values is you take this Y and subtract that, and just make sure, from Excel standpoint, make sure you lock that cell in with F4. Now, you can actually do the subtraction the other way. It doesn't really matter because you're going to square the term anyways. Because what you're going to do is you're going to take I plus A times that squared, and just copy that in, and boom, there's your moment of inertia. So the moment of inertia for this section is 99.73. And if you go back to the slideshow, look right here, that's what we got. So it's the same thing. It's just me going through it, with a little bit of more detail there. I actually do kind of like this image because I want to show you. Remember, the centroid from the bottom is like 13.436 inches. So there is a different extreme fiber distance for the top and the bottom. If you look right here, what you see is, the extreme fiber distance from the bottom is just the centroid. Because that's where we measured the datum from. Remember, we expressed all our distances from that bottom surface. So when we computed Y bar, it was measured from that. So my extreme fiber distance from the bottom is just Y bar. For the top, however, it's not Y bar, it's the height, minus Y bar, okay? So we take the total height of the section and we subtract Y bar so that we can get that C for the top. So if I go back to my Excel, what I can do is I can say, okay, C top and C bottom. C bottom is just that. C top is what I'm going to do is I'm going to take the total height, 1.25 plus 32 plus 0.75, and I'm going to subtract y bar. So that's where I get the C top and the C bottom. For the S, for the section modulus, because this is not symmetric, I'm going to have two of them. An S for the top, and maybe I should use underscores there. So S bottom. And so I just take that divided by that, and that divided by that. And if I'm trying to compute the yield moment, typically what I do for the yield moment is I'll take the yield stress times just the minimum of these two, because when we're computing the yield moment, we're trying to figure out what, what's the lowest one, what's going to hit yielding first. So we just go off the minimum one. And then if you remember from the plastic moment, we're going to divide by 12 so that it's in foot kips, and we get 20.86. So, where'd my mouse pointer go? There we go. So going back to the presentation, you can see this is where a lot of these values came from that was on this slide. So you can see that, if we summarize everything for the beam, we've got our plastic behavior. We got the plastic moment of like 2,700 foot kips compared to a yield moment of about 2,000 foot kips. Again, the plastic moment is always higher, just as the same thing with the Z value. We got two different, we have a Z value of 648. We have two different S values, but what really matters is the minimum. So the Z of 648 compared to the minimum S of like 485. Again, Z is always bigger than that S value, just as MP is always bigger than that MY. But the really big kicker is, and what I find to be kind of the most interesting, is comparing that to that. Because the section is not symmetric, the neutral axis moves. It has to move in order to maintain equilibrium. In elastic land, the equilibrium is found, just by locating the centroid. That's where the neutral axis is. But when we're looking at the plastic moment, that neutral axis, that center location, if you will, it moves so that the compression equals the tension. And so they're not in the same spot. So it's just a really interesting find. Okay, next time we're going to use some of this stuff, particularly a lot, just looking at the Z values, but we're going to use this stuff in order to compute the capacity of rolled shapes. The other final observation, just to summarize everything, whenever dealing with symmetric sections, when they're symmetric about their axis of bending, the elastic neutral axis and the plastic neutral axis, they occur at the same location. We only have one S value, and MP is always larger than MY. When dealing with non-symmetric sections, they don't occur at the same location, specifically not symmetric about the axis of bending. I did have one other thing I wanted to mention, and that's about some of the stuff in the manual. If you ever look up sections that are non-symmetric, like angles, there's something that we kind of glossed over, and I told you a while back, I said, I will explain this, that if you look up, for example, angles, you have a Y bar, but then you also have a YP. And I said, just ignore that for now, but that YP is related to beams. Well, here you go. Y bar is the location of the centroid. YP is where the plastic neutral axis lies. And again, technically the plastic neutral axis is where C equals T. The only other thing I think is worth mentioning is that we don't really care where we don't really care about ZX if the section is not made of the same material. ZX is really only a useful term if you're dealing with a shape that's all one material, like it's all Fy equals 50 KSI. Sometimes in bridges we use sections that have varying yield stress, like we might use a different yield stress for the tension flange. We call that a hybrid section. But we're not going to do that really much in building design, so you don't really need to worry about that in here. Okay, that's all I have, everybody. I will see you all next time. You all have a wonderful weekend.